I'd like to welcome everyone to our IN3 Tech Tuesday series. We do this in support of the Midwest Tech Bridge. I don't know if, for those of you who have met Ann Fields here in the front, she's our Crane, SWC Crane Tech Bridge Director. And we work closely with her, IN3 does, on several issues. And this is a monthly series that we have. And this one's a little different in that we're going to a panel structure for additive manufacturing. I've got four SMEs here. From right to left, I've got Eric St. Hours, I've got Matt Kelly, I've got Eric Schnell, and I've got Zach Leisha. So I'll let them tell you a little bit about what they do and what they bring to the table in the additive manufacturing world. And without further ado, I'll kick it over to them. I have two other just brief announcements though. Let's please hold questions till the end so that we can get through the briefs. And then at the end, we have a collaborative session, and we have lunch, snacks, and whatnot across the hall. Feel free to join, and we can socialize and collaborate there. Thank you. Okay.
Intros first.
Intros first, Eric.
My name is Eric St. Hours. I'm a mechanical engineer, one of the AM POCs on base here. I guess not here, but next door, SWC Crane. I'm in the Airborne Electronic Attack Group, but with the AM stuff, I'm in tune with the NAPSI working group and other efforts up there.
Hi, I'm Matt Kelly. My background is also mechanical engineering. I have all three of my degrees from Indiana University in South Bend, Indiana, Notre Dame, go Irish. I'm currently with U.S. Army Ground Vehicles Systems Center as an additive manufacturing technologist, and my specialty is in metal additive manufacturing, mainly in laser powder bed fusion and large-scale metal like wire DED and additive friction stir deposition.
My name is Eric Schnell. I also have a background in mechanical engineering, graduating from UC San Diego. I'm founder and CEO of Crater. We're a small business out of San Diego working on the development of expeditionary manufacturing alongside the Marine Corps, Army, and Navy through cooperative research and development.
Hi everyone, my name is Zach Leisha. I run Tallman 3D. We supply feedstock to 3D printing users around the world. We have a lot of customers in the defense sector, all the service branches. We also work a lot with state and local governments in the U.S. And I'm here to talk about material science development and different ways that the private sector and services can work together to solve the challenges that we're all interested in solving.
All right, so the slides here, it's a little bit cobbled together from two distro A existing sources, but should tell a pretty good story here. Slide. All right, so just for the group baseline, what is additive manufacturing? Well, surprise, you're manufacturing by adding material, usually layer by layer. What's the difference between AM and 3D printing? They're pretty much synonymous. There's a little more of an industrial professional connotation with additive manufacturing. It's more appropriate, in those type situations. All right, again with the baselining, additive manufacturing. There's 7 different methods recognized by ASTM, ISO 52900. There probably should be a few more added or some definitions tweaked or this or that. And all those methods, I mean, that covers metal, ceramic, polymers. There's hybrids between different methods. There's hybrids with, say, subtractive manufacturing. There's differences in vendors doing the same thing. All those words, lots of acronyms. This slide is actually from 2018. There's more acronyms today if I were to update this. And all that to say is additive manufacturing is not just one thing. It's a broad collection of technologies. And I think you'll have some pictures. This is kind of boring slide. All right, so just in general, AM uses, this is probably kind of goes across the board here, but I lump it into kind of 3 categories. Kind of your rapid prototyping, your end-use parts, your kind of indirect AM, where you're not making the part, you're just helping to make the part. All right, so rapid prototyping, that's the most common historically and current, for use of AM. That's really, I say, the print twice, cut once mentality to kind of save costs, save time. I also lump the training aids in there. A lot of times it's a lot quicker, cheaper, to make inappropriate to make a plastic facsimile versus trying to make another example for a part when trying to replicate function to the fleet. Indirect AM, so really molds, lots of molds. So injection molding, this is all things we've done on base and are doing on base. Injection molding, thermoplastic injection molding, we have good capability on base for that. I put cold mold here, like two-part, polyurethane type molding. That's maybe over molding to protect cables. So it's really into that production flow. We do composite layup molds on Voltem 1010, pretty high temperature. You design it right, it can even take the post cure at 400 Fahrenheit with our system. I think I'm about 50-50 with that though. And then fixturing tooling, just as needed, as appropriate. This might kind of blend into some of the end use. For the next slide, end use parts. That crane, tons and tons and tons of use, in testing applications. Specifically in our group, we have a lot of test benches that are testing boxes, that are testing circuit cards. We have a lot of ABS, ESD from Stratasys. That's one of the capabilities we have. Lots and lots of parts in there. ESD is electrostatic dissipative. You don't want to build up a charge, next to a very expensive SRA or circuit card. And airplanes, geometry that it's kind of hard, to manufacture in different ways. Fleet support, we do have quite a few parts out there, covers, caps, this and that. What I'll call the operational parts on the way. As I said, this is from 2018, the slide deck. It's still on the way, unfortunately. We've got a few exceptions here or there. And I'm talking about NSWC crane, not necessarily, in general, but hopefully we'll get past that pretty quickly. This is just an example, 2015-16 timeframe, where we had to make a cast aluminum air manifold. Well, we own the tech data, but we didn't own the casting patterns and this and that. And the casting house, had an NRE, to remake, these 3 different types. Well, we looked at it, they didn't need to be casted. They were just in a test bench. And so we were able to print on the ESD material, save over 100 grand. And that's a low ball there at that 105K. And we've been using that for every test bench. Other than this, going forward, plenums are a great application area. All right, switching to the NAVC distro brief. This is kind of current, 4 kind of initiatives here. The tech authorities, really, I'd say tech pubs, and I'll speak to that the next slide. Then kind of the ATS-CAM metal is coming, is being installed right now, 2 slides away. Digital integration, really that's the tech data, how do you store that and how do you access that securely. Then supply system, that's kind of self-explanatory there. There's some neat pictures top right, including one that was put on a carrier. Does that see the end? Yeah. All right, tech authority, tech pubs. So there are 2 tech pubs currently released in NAVC. There's a laser metal powder bed fusion and a directed energy deposition, both metal. There's also in review right now, so I just reviewed a material extrusion for polymer, so FDM, FFF. All 3 of those, the material extrusion will be released at some point here quickly. This has been used mostly internal for NAVC and the kind of organic industrial base, if you will. But the whole point of this at a certain point is to make sure, that the material, the process, and the part can be qualified so an external vendor, can build that for us. That is still ongoing on how that will eventually work. But I can speak to that during some questions. Chipboard, metal AM. So the USS Bataan LHD 5 is not, they aren't getting, it is on board and is getting installed right now. This is a wire arc directed energy deposition. system. And as installed, it's in a traditional 3-axis mill. So it's a hybrid type setup where you can do additive manufacturing, then come back and mill it to final shape. And you can see a picture kind of in the middle there on the left. Looks awful, you know, not really functional. That's near net. You know, you're putting that close to the final, so all you got to do is machine off, you know, the last 5–10%. You know, drill a few holes in that case, and then, you know, an example at the bottom. Fire spanner wrench. This is actually something that's approved for polymer, depending on, you know, the materials and that, but great application. You know, obviously, metal on board ship opens that envelope to the number of applications, number of useful applications, but there are a lot of issues, you know, shipboard with a lot of the metal, you know, additive manufacturing methods, you know, practical and environmental type issues. So, all right, this is the last slide here, I think. Just some metrics here. 94 NSN, National Stock Number parts as of April. I saw an updated number. It's more than that now. And of those, half have a cost reduction, but all of them have a lead time reduction. The supply system is a beast. Everything takes forever. And you can see over there, 42 days is the average lead time. Anecdotally, I've heard 6–9 months for a cap, a little wheel, and that's something that's actually taking down that system because they need that cap, that little, you know, knob or wheel. And so AM in that case, and we're talking all polymer, pretty much all polymer here. There might be a metal, a few metal examples in this, but mostly polymer. And the last thing I'll mention, there are actually 300 approved technical data packages now in existence. And I think there's more than those, about maybe 500 parts in there. So some tech data packages have more than one part, but that's growing and growing as well, and will grow from polymer to metal as some of those processes kind of mature within that state. So I hope, save your questions, I guess, till the end, but a little cobbled together, but I hope that gave a good overview. We can discuss a little more afterwards.
All right, thanks. So I'm here today to talk about the project that I've been leading with U.S. Army Ground Vehicle Systems Center. The last 8 months or so, I've been in the lead role for this project called Jointless Hull, where we are enabling rapid large-scale metal AM for Army ground systems, but more broadly for the DoD and also commercial industry. So I'm going to give some overview of the program, go into some basics of what large-scale metal additive manufacturing means to us, talk about the capabilities of the machines that we're building, the materials that we can print with, and how to engage with the program. So why is this program called Jointless Hull? So traditionally, vehicle hulls for Army ground systems are manufactured by joining multiple plates together at the seams to create joints. And those seams are potential failure locations for our soldiers in the field. So the idea was if you could manufacture one of these hulls monolithically, you would avoid those failure points and increase survivability for our soldiers. So that's the naming behind the project. But it started back in December of 2020. So U.S. Army, GBSC, TACOM, and Astro America released an RFI to industry, challenging industry to come up with capability that was able to manufacture a vehicle hull in a single manufacturing unit cell. There was no commercially available metal AM systems at the time that could manufacture parts of that scale. And we wanted to utilize this, right, to enable weight reduction, elimination of joints, increase the speed of the design cycle for these large-scale parts, and improve overall performance of these vehicle hulls. More broadly, though, for this group, when we talk about this manufacturing capability I'm going to show here, we're speaking about direct manufacturing or repair of what would traditionally be the casting, forging, or a weldment. So you can see the two machines here. I'll go into more details for each one of these machines on a future slide. So just to touch on the 7 families or categories of additive manufacturing that Eric introduced, most folks are aware of at least material extrusion here on the left. There are some material extrusion machines back there. Those are your desktop 3D printers, all the way to production like FDM printers. You might be familiar with SLA, which would be in the vat polymerization family, stereolithography. The projects or the technologies that we were considering for what our requirements were, which was at least a 20 by 30 by 12 foot, or at least a 20 by 30 by 10 foot manufacturing unit cell. Most of the submissions that we got, or the responses, were utilizing technologies from the directed energy deposition family. So those are your wire DED processes, a process I'm going to talk to you about called additive friction stir deposition, which you could actually think that technology might be material extrusion in a way. Sheet lamination, you can also do large scale metal AM, but it's a lot slower deposition rates because you're putting together multiple very thin sheets of material on top of each other. So what is large scale AM, or metal AM? To us, it's anything greater than a meter cubed. So that kind of rules out most powder bed systems due to the economies of filling a large chamber full of powder, right? So again, I kind of just talked about these processes that support large scale metal AM. The technology that we've integrated into the manufacturing unit cells as part of the Joint Whole program today is called additive friction stir deposition. It's also known under its trade name, MELD. In this process, so in this process, it's actually very unique. Additive material, and in case of melt machines in our equipment, it's square half-inch bar stock. And metal bar stock is forced through a cylindrical tool while it's rotating. The friction between that metal bar stock and the substrate below heats up the material enough to where it will plasticize but not melt, right? So it's malleable, but it's not melted. And it's deposited in about 1.5 to 1 to 3 inch widths, about a millimeter size layers. You can go higher too. That's in general the scale you're at. So again, this technology can be considered DED material extrusion as far as the family. So like you said, the definitions kind of have to change as technology progresses. So what are some of the advantages to this process versus maybe some of the wire DED processes that we traded against? So it's a solid state process, meaning the material never melts, which gives you some advantages in that you don't have solidification defects going from a liquid to a solid, where you have porosity, no cracking or hot tearing, things of that nature that arise due to melting. In some cases, because it's not at melting temperatures, you can join dissimilar metals together. So you can think about direct manufacturing or repair applications for joining together two different materials that have two different melting points and chemistries. And because you're not melting, you have lower heat input, which leads to lower residual stresses and less part distortion. So you hear about welding together large parts here, and even with laser powder bed, you hear about material lifting from the build plate because of the residual stresses induced by thermal distortion. That you don't have that issue, or it's much less of an issue. And also, there's just a wide variety of processable materials. There are some materials that are unweldable that you could process through additive friction stir deposition. It's solid feedstock, right? So same advantage as having the wire, right? You don't have to handle powder, and therefore it's kind of less expensive compared to wire and powder. It's high throughput, so for some materials, build rates of up to 40 pounds and greater have been demonstrated, and we think it can scale even further as you develop different high torque machines. And it's scalable, obviously. It's very large parts. We have a machine designed to print parts greater than 30 by 20 by 10 foot. Some disadvantages though, right? What's bad about this process? Very poor complexity with our machines at the moment. Your deposition widths range between 1.5 to like 2.5 inches. So any thin wall structures that you're designing for will likely have to be post-machined and require significant post-machining and waste. There's limited production capacity currently. Meld, I think, has sold on the order of tens of machines. A good amount of those are in universities So there's just limited production capability. So if you have large quantities, it's going to be very difficult, especially for large parts or the only machine of this scale available. So your quantities are going to scale, your lead times are going to scale linearly with your quantities. There's also a limited understanding of material process property relationships. It's a relatively newer additive manufacturing technology, so there's less data available for tensile and microstructure, for example, generated in various deposited and or heat treated conditions. There's also very limited fatigue data available at the moment. So what are some of the other large scale metal ion processes? I mentioned the different versions of wire DED, depending on your energy sources, a laser versus an arc, a gas tungsten arc or a plasma arc, or an electron beam. Right, disadvantages to these processes are mostly arise from the large thermal input and the melting that causes. So you have a limited material selection with this additive process. Your parts are more prone to geometric distortion, residual stress buildup, but you can achieve smaller feature sizes. Standard bead widths are about 1/4 inch. So you can achieve greater complexity and in some cases less post-machining. So what are our machines capable of? This is the jointless, what we call jointless hole. It's our whole scale tool. It's capable of building parts 30 by 20 by 12 foot. It's a hybrid machine, so it can both print material and subtractively remove material via a 5-axis machining head with an integrated tool changer. This machine will be operational in June of next year, and it will be located on the Rock Island Arsenal in Rock Island, Illinois. It's just on the border between Illinois and Iowa. The subsection tool, it is capable of producing parts roughly 1 meter cubed. This machine will actually be located not on any Army base, right? It'll be located at an SAE facility in Sterling Heights, Michigan. It's called, we call it our Advanced Manufacturing Commercialization Center. So this is an interesting place to house this capability in that it's not necessarily as closed off to industry as getting onto an Army base to see a machine. So it's a little more accessible to the public. And it will be operational in March 2023. It is almost, it's functionally the same as the whole scale tool outside the scale. And that was on purpose. Because we want to encourage folks to utilize the subsection tool, not only for parts of smaller size for production, but also to use it for early development of the technology before transition to the whole scale tool. So again, they were designed to be as similar as possible. So they have the same melt deposition head, the same milling spindle, same machine software, same build prep software. So besides scale, you're going to be able to transfer right from one machine to the next. So it's called the subsection tool because we intend to build subsections of parts on that machine just to prove out tool paths, etc., according upon the large machine, which is obviously more expensive to operate, but can achieve far greater scale. So again, on the subsection tool, we plan to do things like develop process parameters, tool paths, do experimentation on different part geometry features, and then transition all that knowledge to the whole scale tool at Rock Island Arsenal. So the materials that we're initially interested in are 7,000, 5,000, some 2,000 series aluminum alloys, titanium alloy Type 6-4, and a couple 4,000 series steels, and then HY80 as well, which I know the Navy is interested in. I think over the next 5 years, the Navy will account for over 50% of the casting demand for the DoD, and that's largely due to the Virginia and Columbia class projects that are ongoing, and they utilize a lot of nickel and steel for their castings. I think it's greater than 45% of forging. So we do have in mind, right, multiple DoD partners that we want to collaborate with this capability. And this is just a list from Meld, which is just showing what materials that they've demonstrated this technology being capable of printing. But this is not obviously the limit of what you can do. Your availability of material does depend on the availability of the bar or the plate for you to make bars out of. But anything that can be melted into a half-inch bar can be processed via AFSD. Okay, so this is a demonstration of capability that we're creating, that we did as part of the Run This Whole project. We took what would traditionally be steel forging for the Bradley vehicle. It's for a hatch, so just a hatch that opens right for pulled in and out of the vehicle. So we took a hatch, we redesigned it so it's public can view it, right? We generated a print file, we printed it out of 6061 aluminum. You can see it in the top right here, printing on an existing piece of melt equipment while we're obviously waiting for ours to be operational. And we did the machining setups outside of this machine because it's the machine we printed on is not hybrid. We printed it. It took roughly 30 hours to print. If we were to print it again, it would take 30 hours. And machining obviously took longer than the printing. This part in its fully finished condition weighs about 180 pounds. And it was at AMUG last year. It was at DMC last week. So yeah, this part kind of travels with us on the road. It's roughly 3 feet. We built it roughly 3 feet tall, and there's about 3 feet wide and about a foot deep. We didn't optimize the orientation for build time, and we optimized it for let's show how tall we can build. But this is a unique part here that is difficult to additively manufacture without this technology. All right.
Thank you.
On the pointer.
Sure. I don't know how much I'll use it.
Yeah.
All right. So once again, my name is Eric Schnell, founder and CEO of Crater, and I'm going to share a little bit of kind of where we came from and some of the collaboration we're doing originally with the Marine Corps, but now also with the Navy and the Army. So originally our team started as a group of student engineers out of UC San Diego. We were first introduced to the digital manufacturing unit out at Camp Pendleton. This was one of the first units that first started to tackle the problem of how do you actually leverage 3D printing in an expeditionary environment. They were stationed at what would eventually become the prototype for the XFAB, if you're familiar with that program of record that currently exists. We spent about 6 months working with them. Everything from part identification, reverse engineering, process and procedure development, and finding what 3D printers that exist on the market that can best meet their needs. Problem we saw with our time there was that 3D printers were often failing kind of where they're needed most, in those expeditionary environments. And the Marines were spending more time working around the limitations of additive manufacturing than the 3D printing companies were willing to spend time on actually making a system that worked for them. So that's kind of where our company came in. We formed Crater and started developing an expeditionary solution for their needs. In November of 2020, we actually formed a CRADA, Cooperative Research and Development Agreement, with the Marine Corps for 9-Week Pacific. The focus of the CRADA there was to conduct on-site collaboration and mutual technical exchange and enable this continuous dialogue between government, academia, and industry. So what that practically meant was that we actually were moved on to Camp Pendleton. Our office became a 20-foot expandable shelter at 9th Com Battalion, where we worked with Marines every day in January of 2021. And since then, we've been embedded in over a dozen field exercises across the United States, from operating the high Sierras at sub-zero temperatures at Mount Warfare Training Center Bridgeport, to at-sea printing aboard a Navy destroyer out at Port Hueneme, operating at 29 Palms on field exercise out there, and some incoming testing on the air side, Okinawa and Alaska. And we actually had so much success from a lot of the developments there that recently, this last year, expanded to include the Navy through NAVFAC X-Wing and Army through CBC in July 2022. Practically, the last few years for us has been kind of developing through a practical, tactical approach develop, iterate, test, deploy, develop. So what that started with was our alpha unit. So our alpha was essentially a printer in a box. So as you can see in some of the photos here, that's a Pulse by Matter Hackers. It was integrated into a support system to help allow it to print an environment reliably and consistently in most cases. We actually had a good amount of success in that. Deployed it in various different field exercises, printing primarily up to nylon carbon fiber. But we also learned that from that is kind of a Band-Aid solution to what really needed to happen, and that was the building of an expeditionary system. A couple more photos here. An expeditionary system built from the ground up to operate in these environments and print high temperature ultrapolymers in field, which led to our Bravo unit. So our Bravo here is a high temperature capable 3D printer. So we're able to print full temp. We actually have a chambered temperature that's able to be maintained up to 80 degrees Celsius, even in sub-zero temperatures. Be able a 200 Celsius bed, 500 Celsius nozzle, which enables the printing of a lot of ultrapolymers that can be direct metal replacements. Can serve both on the traditional maintenance repair cycles, but also to serve the medical applications and some more innovative focused approaches there. We kind of did the same thing. We developed, tested, iterated, and deployed it along with the Marine Corps, the Army, the Navy, these environments, and really prove out the technology. And now we're actually going into initial rollout of our first product here, which is Intrepid. And the key of that is a 3D printing platform that can print where no one else can. Reliably, consistently, resiliently, in any environment our warfighter finds themselves in. So it's rugged, portable, and it's intelligent, because when it comes to actually deploying this in the field, an incredibly complicated system, you can't rely on having engineers or SMEs out in these austere environments. So part of that has been developing a lot of the intelligence side to it. Now, as a little bit of more granular approach to what makes this system unique and kind of what we have defined as necessary through our collaboration and direct contact with Marine Corps, Navy, and Army, is that at the core of everything, we provide a stabilized print environment that can operate in any condition that will enable consistency and reliability between parts. If you were to develop a technical data package or a TDP that says this is exactly how you have to print the part, but if you're out in sub-zero temperatures versus out in the middle of 29 palms, there's going to be variations on the print capabilities, then those technical data packages become useless. You rely more on the tribal knowledge of the operators in the field to be able to print successfully. We've worked to eliminate that and provide a stable environment no matter where it's deployed, so that all you need is a basic technical data package. Basically, how do I print this? And any operator in the field can print it reliably and consistently and get the same part every time. We're also, as I mentioned, doing high temperature and composite 3D printing. So it's an FFF, if you remember the charts from before, or an FDM-based 3D printer, kind of one of the traditional methodologies. But through that, we're able to do anything from the most basic of materials, PLAs, PETGs, those kinds, to flexibles, TPUs, all the way up to composites like nylon carbon fiber, and including ULTEM. The unique side of that is that a lot of times ULTEM and these high temperature ultrapolymers are exclusively printed on large scale 3D printers. So industrial scale printers, your Stratasys, your Fortis, your Ascension printers that are the size of refrigerators, if not bigger, they're not really able to deploy into environments. So we are the smallest scale high temperature 3D printer on the market, and have the largest print space to use portability of shell space, essentially, of any printer on the market. We're also designed to military standards and modular. So we've designed it to 810G and 461F. We have not certified. That's one of our goals of the coming year. And we've made it modular to enable field maintenance to happen on core systems, are modularized. So in under 5 minutes, an untrained operator can strip down key parts of the system, the brains of it, the power of it, the extrusion system of it, replace it in field without having a contractor out there to do repairs or replacements. We're also the only 3D printer that is successfully printed in all environments for mobile 3D printing. So we've strapped it down in the back of an amphibious combat vehicle and did an amphibious approach over at Del Mar in San Diego, printing the entire time and shaking around the back with 100% success. We also deployed it on Navy destroyer over Port Hueneme, printing all the while underway. I mentioned a little bit of the intelligence side. We actually integrate machine learning-based quality assurance. So every single one of our parts actually prints with a report, a quality assurance report, that connects back to the technical data package that has been established by initially the Marine Corps, but is now being used across all the different services. Basically verifies the part printed to spec to the technical data package. Now, all these capabilities are capabilities that basically been defined through our collaboration. They've been integrated out of need and out of basically testing and iterating, and not a few failures. So, but we've actually seen significant impact. So when it comes to, and we've already heard a little bit of some of the impacts of overall additive manufacturing. But what we've seen in the field, we've seen kind of firsthand on the expeditionary side. On average, we've seen a cost reduction anywhere from 10 to 100x on a lot of the parts that we're manufacturing. So that's parts typically in expeditionary environments that range from communication systems, power generation, power distribution, weapon systems, and various other capabilities. We've seen a vast increase in readiness and sustainability, sometimes over 100x. In many cases, bringing legacy systems that still have to run for the next 10 years out of deadline that we're going to be potentially permanently hangar queens and parted out for other things, but we're brought up and running themselves. And we've also seen opportunities to use advanced innovation to help solve problems. The Marines often joke about if you give them a roll of duct tape, a chisel, and a rock, they'd be able to solve any problem. You can imagine this is the new duct tape, especially in this expeditionary environments. It's an option for them to be able to innovate, create solve problems in field environments where they don't have access to capabilities here domestically. We're able to also adapt to mission constraints and environmental conditions. We're deployed extensively on this end with SOF, Marine Corps and the Army, being able to customize kit and fields to optimize for specific mission constraints and enhance the long-term sustainability. Part of that includes on the medical side, given that we can create full-time, which is biocompatible material. It's also a high-temperature material, which means that we can actually sterilize it in the field through traditional means, steam autoclave, and can actually print limited or single-use surgical items and various other medical equipment. In fact, right here, you can see a open source design that is currently being used in Ukraine as 3D printable, 3D printable tourniquets. You can also do the same with pressure bandages as well. Now, when it comes to, we mentioned modularity, and reliability and resilience is kind of a key here when it comes to 3D printing in general, right? Or using 3D printing to help solve our reliability and resilience problems doesn't really work if that 3D printer is incredibly complex, difficult to operate, and difficult to maintain in field. So part of that is the modularity that I mentioned. But also part of it is the ability to be able to be upgraded over time. We've seen that 3D printing changes almost by the day. For looking at some of these presentations, you can see that there's been vast changes. Part of that is hardware and part of that is software. So modularity also enables upgrade over time, supporting kind of long-term mission. A lot of this is being figured out when it comes to deployment within the DoD. We're still really at, well, to be honest, the technology is in its infant stage here. I mean, we're really just at the cutting edge. And so enabling a system that can be upgraded over time is definitely important to us. And it's only part of a bigger ecosystem. So we provide the most far forward, the edge of manufacturing. But 3D printing is best deployed at multiple different tiers or multiple levels of an ecosystem. That could be depot level manufacturing with large scale metal 3D printing, large scale polymer 3D printing, or in some of the cases that we've talked to already here, at a contractor level for deploying kind of new assets that wouldn't exist without the capability of 3D printing, or all the way out to the edge. So one of the things that we look to here, along with our collaboration with Marine Corps, Navy, and Army, is to be able to generate a system that can tie in with other systems, both software, minimize training, minimize operator complexity, so that at the end of the day, an operator can come to, for example, a large-scale Ascension 3D printer that can print polymer parts up to 9-foot cubed, or our printer, and be familiar with the ecosystem, the slicer, the technology, and also the quality assurance package. And that's just part of kind of the effort that we're doing with the our credit here. And this is kind of just the beginning, as I mentioned, for us. This is a technology in its infancy. We're learning more and more every day. We're developing every day alongside our partners within the DoD. But our long-term vision here as a team, as a collaboration, as both inside and outside the government, is to enable the decentralization of manufacturing and supply for a more efficient, reliable, and resilient supply chain, no matter what the future has in store. Let's cut to this, a couple of the photos, and then I'll pass it off to
Thanks, Eric. Thanks, everyone. So I wanted to start by talking about the value proposition of additive manufacturing. It's been touched on a little bit here, but the reasons why it is so useful, lead time was mentioned earlier. That's really a big one. There are OEMs that aren't even in existence anymore that, basically you can't source the part. So even if you can get it, it could be 6 months. So really the technology can be applied to bring systems back online much quicker than if you had to rely on traditional OEMs and traditional manufacturing methods. That's really a big one. In some cases, it can be a cost reduction mechanism. That is not always true, but it's certainly worth looking at the technology for that purpose and then doing your analysis to figure out if that's true or not. The third one is a bit of a holy grail, and that has to do with changing the geometry of the components themselves. The private sector and the services are doing a lot of work right now to try and develop some of these technical data packages for the parts themselves. So there's not as much work being done there. But once we can build up the library of parts to decrease the lead times across thousands and tens of thousands of parts, then we can get into the work of actually changing the geometries of the parts to make systems lighter, more energy efficient, and more lethal. So that's just the general value proposition of the technology in general. And then to speak to you about Tallman, my company, we're based here in Indiana, in Linton, Indiana, and we're known for providing the feedstock for 3D printed parts around the world. We've been doing this for about 10 years. We do carbon fiber nylon, glass fiber nylon, medical grade materials, FDA approved polymers. So our feedstock is used quite a bit in the public sector as well as in the private sector. And I wanted to focus a little bit on how those two groups can be put together to provide value add for the country. Using Tallman as an example, we've been providing the feedstock to the services in a passive approach for years, where they were simply purchasing our materials to create parts for their needs, and really we weren't much involved outside of shipping it from Indiana. And we were connected to IN3 and TechBridge, and that allowed us to work more with the Navy on some of the benefits we thought we could provide to them, and then they were able to assess whether that was actually worthwhile. So this is an example of, for businesses and for companies that have value add for the services, there are mechanisms to reach out and provide solutions to potential problems. think that there aren't a lot of businesses around the country, or enough businesses, thinking about that, especially in the additive manufacturing space where there's a lot of interest. If you feel that your technology or your product or your service might actually be useful to the needs of the services, reach out to, there are a lot of tech bridges around the country, so you can reach out to them based on a regional basis, and you can actually find out if your solution is deemed worthwhile by the services in your area. And the flip side of that is there are a lot of teams that are sourcing additive manufacturing systems and materials and feedstocks, but they don't really know how to do that at scale. So Tallman 3D has been successful in creating different channels and different mechanisms for the services to procure our products. So if you feel there's a particular 3D printer that you like, or there's a particular 3D scanner, or there's a particular brand of material, or even a specific material that you want to get your hands on, but you hit your P card limit, or you just can't find it, you can work with the DLA to ask them to create something called a national stock number, which is something that we have. We hold the only NSN for nylon feedstock, and that basically allows teams around the world, Japan, here in the States, really anywhere, you name it, to source what they need at greater scale. And I'm only mentioning this because when the teams that we've worked with across the services have mentioned that they often have a need or a desire to purchase our products, but they can't cut through the red tape and figure out how to actually do that. So I think it's important for the private sector, when they have solutions for the services, to reach out to the different tech bridges around the country to offer their solutions, and then you can figure out if it's actually worthwhile. And it's also valuable for teams around the different services to engage with industry if they feel that they want to procure something that they can't currently do. There are mechanisms such as the DLA, where you can reach out to a tech bridge as well, and they can grease the wheels on making it easier to procure these sorts of items. So I just wanted to keep it short and sweet, and that's really all I have. But if you are 3D printing different components, whether it's in the States or around the globe, and you're creating technical data packages, you should know that Tallman is already verified in a lot of these packages, and we manufacture everything in the United States, here in Indiana, to maintain our supply chain integrity.
Thank you, Zach. Thanks to the panel. At this point, I'd like to open it up to questions from the group, and if you have a question, please speak it loudly, because we have folks that are listening in on from the virtual world, and that they can hear your questions. So at this time, opening the floor to questions for any of our panel members. Yes, sir.
So in regards to the jointless hull, what do changeover times currently look like between jobs? So I'm assuming that you get a print, this I guess can go for both focusing on the additive manufacturing side as well as the implementation and subtractive side that's processing.
Yeah, so the question,
Yeah, if you're going to repeat the question, that's a good thing. Thanks.
So the question was, in regards to jointless hull, what are some of the changeover times between producing one part to another part? So it's relatively simple to change out your material. If you were utilizing a similar alloy, you can generally use the same tool to deposit that different alloy if it's in the same family. But say if we're switching from aluminum to a steel, we have to change out to a harder tool to deposit that material. And I mean, that's still in the order of minutes. You would be building directly onto build plates that are clamped to the table below. So if you were going to fully machine your part right after you deposit it on the platform itself, if you were able to do that right in one setup, then you would just machine it, and then you take a crane and lift off that plate from the line to where you, an area where you either bandsaw off or remove the base plate from some other method. Or if you were integrating your build plate into your design, then you just machine the contours of that away. But yeah, as far as like, you're kind of just limited by how your kind of your cranes in the area to move parts out of the area. The large scale machine that can be used to build the 20-foot part, but to make it up, it might also be used to build, 30, 2-foot parts, right, in different areas of that manufacturing unit cell. So you could be building one part over here, move your cross rail to the other side of the machine, have your crane come in, lift that part out, and then move it back and forth, right, and continue operating your machine so there's no downtime.
Kind of as a follow-up to that, you mentioned that there's different organizations that will be taking advantage of this machine. How does that, who's managing that queue and the value stream?
Yeah, so for the full-scale machine, Rock Island Arsenal will manage the utilization of that machine. So I would imagine they would prioritize applications for the Army that are kind of based out of that region. But then beyond that, they would likely give the priority, and this would be I'm speaking for them, but my guess is it would be Army, DoD, commercial industry. Yeah. And then for the machine that's going to be in Sterling Heights, Michigan, the smaller one, it's still GVSC owned, but it's located at the AMCC, the Advanced Manufacturing Commercialization Center. Again, we want to support the large-scale machine as much as we can. That's what this project's about. But we do want to utilize the machine 100%. So we've already seen quite a bit of interest from industry. It's not just within the DoD. And so, it would be reaching out to the folks at SAE to get time on that machine.
Thank you.
Yep.
So, St. Howard, you were talking about the 90+ tech data, or 90+ innocent files and the tech data packages. So, where are those located, and who has access to those?
So the NSNs, those are just, I know there's some databases, accessible to pretty much everyone that you can go in and look at those NSNs. So that's just basically the listing. Now the tech data that is not publicly accessible yet, there might be a certain, portion of those that could be, but that right now lives on a platform called JTBI for NAVC at least. There might be a few other pockets, but I believe that's the official DDP repository. That anybody DoD can get, anybody Navy can get. Yeah, DoDJ is joining. Could probably get access to that. It's just getting approval from the right people.
So I guess to base my question, so I'm the software cyber task lead at Frame, the XDev.
Okay.
Right. So currently they use Windchill to go out and pull parts. I didn't know if those SNs and tech data packages are, hey, you have to go buy this and pull it down, or if they're just part files and reads go out and grab somewhere and they can print them at their shelters.
Correct. And the Marines had it was like a maker. There was another thing I had access to it at one point.
DMDB. So the Digital Manufacturing Data Vault currently has 400 green bin parts, with about another 200 that are yellow, which just means they're waiting for approval. Those are actually currently accessible. So if you're associated with XFAB, you should have be more than able to link up and get access to that with just a CAC or ECA cert. If you need introduction to the people who are managing that, just let me know afterwards. I can make that joke.
So what was it called again?
Digital Manufacturing Data Vault, or the DMDB.
JTDI, I mean, you could get access to it and pull everything down, if you had just some sort of provision control, you pulled it down this date or whatever, might not have the latest and greatest. And NAVC, that is one of the, part repository with the, digital efforts going on, to maybe more streamline, the accessibility of some of that data. I don't know, NAVSEA versus NAVAIR versus Marine Corps versus Army, someday maybe we'll get, the J is joint, but right now, NAVAIR and NAVSEA daily, that's a JTBI only. And that's green box and, kind of the blue box, higher criticality. This part's mostly found.
On the joint side, they're working on JAMX, which is being run by DLA, which is supposed to be, the intention is that it'll be a joint repository that kind of links independently to the different service repositories. So different services can choose what to share and how to share their technical data packages. That's still a little bit of a ways off though. JAMX, I believe JAMMEX. I might be wrong on that, but it's the Joint Additive Manufacturing Part Exchange.
So, a couple questions. One, Eric, do you know if the undersea community is teaming with the surface community or the air community related to sharing what they're doing or working or how they're qualifying parts?
So undersea, that's still NAVSEA. So I would say there's a better, for NAVSEA 05 is, 05T Technology Office is kind of managing that.
So they're managing the undersea piece as well?
Correct. There might be some special, like subsafe, there might be some requirements where it's still under T, but there's other technical warrant
So
holders
Justin
in that.
should know.
Correct. Justin Retaliata is the technical warrant holder for additive manufacturing for NAVSEA. Then the NAVAIR side, there's definitely, collaboration, there's discussion, they talk, but NAVAIR is NAVAIR, so it's kind of separate. It's almost a separate mill depth, sometimes. But,
So, sort of for you, I'm guessing your machine is FDM?
Yes, yeah.
Okay. So as you're moving forward, trying to get it in as many environments as possible, do you see the next step is to go to another printing type, to have other materials to be allowed in those other very challenging locations? And if so, what do you think the next step or the next printer type may be? Try and get closer. All the admirals and all the people in the world would love to be able to print parts and screws and metal, I'm sure, and make it one size fits all inventory warehouse. But knowing where you're at with FDM, I'm curious what you think the next material set or printer type would be, and then how long you think that horizon would take to get to that step.
Absolutely. So FDM was originally selected because it is actually one of the easiest to transition to unstable environments, adapt to shock and vibration, and be able to actually print on the move. So that's kind of why we initially started with FDM. But you're exactly right. There's a limit to the kind of materials that we're able to do and kind of the long-term horizon. Now, we have seen metal come to the FDM space through products like the Metal X or Desktop Metal, or more open source BASF material, which is essentially a metal powder that's bound in a polymer, printed through a traditional FDM method. We've actually printed some BASF materials ourselves. And that process requires, it's a three-part process. You print the green part, you debind that part, and then you sinter it. So that process requires, the debinding stage there is the other limiter, and the sintering, but primarily debinding is another limiter to making that process expeditionary. The debinding process requires extremely caustic chemicals to be able to actually eat away the plastic within the part before you actually go to sinter it. We are working in collaboration with a couple groups to actually bring in a new form of printing metal. I can't talk too much to that quite yet, but we're anticipating, hopefully, should we be able to secure some R&D and development dollars to be able to introduce metal into the expeditionary side within the next year to year and a half, using the same frame that we're doing now, just with a couple modifications to the extrusion methodology. Still means that we have to bring sintering into the field, but that's already somewhat of a solved problem with kind of bringing welding capabilities out and some of these other things that already exist into environment. So it's a solved problem as opposed to moving a lot of these castings.
Does it solve the problem to get the heat, or do you control the temperature so the density can be uniform? Welding isn't usually.
Sorry, I skipped over a step there. The moving of the cost of this step 2 and step 3. Step 2 is one that we get to hopefully skip over with some of the developments we're working on. Step 3, the sintering is still going to be required, and the problem with sintering is that it typically requires a oven that has a shielding gas on the inside of it. But when it comes to deploying this into an expeditionary environment, the issue of moving compressed gas and shielding and a lot of this other kind of complexities added into an expeditionary environment are solved problems with existing process and procedures typically used for deploying expeditionary welding capabilities. So we've got a roadmap ahead of us to be able to deploy metal capabilities.
The support materials around the process are there.
Exactly.
So you do see in the Army side in the expeditionary environment Connex boxes that have like 3-axis mills in them, and there are companies that are selling basically just wire deposition heads that you can, augment your mill to accommodate, so you can lay down some material and then mill out the shape you need. So that's being done. I've seen concepts using additive friction stir deposition where you could take a damaged door that may have suffered a blast or some ballistic damage and spread over material over that area, right, to close up that door, get that vehicle back in the field. So there's different, there are definitely different concepts out there, and some of them are out there being tested as we speak on the wire
Cold
side.
spray mostly, or
So cold spray, yeah, is that
Speed 3D, they're all over the news, all that. They've kind of demoed that,
Yeah.
In Australia, or an Australian company, and there's been some look, at the Navy and that.
yeah, but like you said, just like people don't want to carry gas, people don't want to carry powder either. So it becomes a challenge when you do that.
And a lot of those systems are semi-expeditionary. So
Yeah, it's cold spray you need.
Conex container.
And there is,
Helium or
yeah, I think Speed 3D, they're actually doing it in open air.
yeah,
So
speed 3D is different.
Yeah, but
There's still
generally,
powder.
cold spray, you'll have, shielding gas in, but, the Meltio system, the reason why that's, being kind of chosen, for on board is, the environment, the gantry type based system, but, sure, you still have the gas, but it's basically just shielding on there versus powder bed, where it's continuous and you might not have any, recovery. Argon, they generally have, some of those materials already on board for the welding, so from the supply. There might be a subset of materials, I don't know, the 316L is one where nitrogen could be used as a purge gas. Maybe that's a bad idea for that one, but now you can just buy a nitrogen generator, so there might be certain materials where the knockdown or the defects, for just using nitrogen, are known, so, I don't know where I was going, but, there is a reason why that was kind of chosen as the first one. That doesn't mean there's not some other technologies in that are worthy of being looked at in the future for that type of environment.
So when you looked at their list of materials that you're machining, you had an interesting mix of, you actually had copper tungsten as one CUW. So I guess my question is, how do you go from that extreme of a malleable low melting temperature to doing tungsten?
So that material is outside my area of expertise. That would be more of a question for folks who've actually experimented with housing that material. That's a list again from the OEM that owns this technology. So I wouldn't know the deal behind using that material as technology.
Anyone else in the group?
This was awesome. Thank you guys all so much for your time. Kranar, I do have one question for you. So you mentioned there was an opportunity where you were on a destroyer at Port Hueneme. Was that Coastal Trident?
It was associated with it, so RepDex,
Yeah.
if you're familiar with it. So we were
Awesome.
attached to NCMS for the RepDex event. We did a few days out at sea and at port printing for overall 2 weeks out there. So we were actually working with Speed 3D and Essentium, doing a lot of part generation out there.
Was it the ship itself, the ship?
Yes, it was, yeah, the test ship there.
Anyone else? Questions for the group? If not, okay, sir, go ahead.
Just one. So, for you, sir, I did, first off, I didn't even know your company existed. You guys are right down the road.
Yeah, Linton. Yes, sir.
So, are you guys just supplying plastics, or are you
Yeah, we're
supplying
polymer
metal?
specialists. We've been doing this for about 10 years. We became well known for a couple of reasons. Number one, we were very early into developing materials specifically for AM processes. About a decade ago, and even more recently, there have been a lot of companies out there that have marketed AM feedstock, but really it's just injection molding feedstock. We kind of understood that early on, so we started developing different nylons. There also were not a lot of nylon suppliers out there at the time, and nylon checks a lot of boxes on the polymer end, especially for the services. So we were early. And we also developed specifically for AM processes. And what happened on our end was the engineers talked to each other. You know, what are you using? What are you using? And we really did focus a lot on our quality controls and making sure that the materials worked very well. And we did that on higher end, more expensive systems, and then also lower end systems. We test our feedstock on expensive and cheap systems so that we want our materials to be accessible. It's very important to us. So once they're released, any type of user can use them. And thankfully, by focusing on quality, the engineers, through word of mouth, began recommending our materials. And then we took that information from them. This is what we would like to have, but don't have. And we began factoring that into our product development. And then also, there was a focus on manufacturing capability here in the States. Through some work I had done with a Dutch 3D printing company, I became aware that nearly all of the filament production was over in China. There really wasn't much here in the States, so we made a conscious effort to make sure that we had something here that ran well, and that's actually right now based over in Linton. And that's the general history of the company. One thing I didn't mention earlier on that I would like to, that Eric also mentioned, was the CRADA. So we also have a CRADA with NSWC Crane, which is a very useful tool both on the private sector side as well on the service side. I was talking about trying to merge capabilities and challenges to solve problems. CRADA is really an excellent way to do that. As an example, we knew that more and more TDPs and parts were being created throughout the Navy, but we also knew that there wasn't a lot of cataloging of some of the RF properties around AM feedstock. They had a pretty significant library on the injection molding side, but not on the AM side. So as additive manufacturing becomes more utilized and more popular, the services need to understand exactly what they're working with on the material property side and the material science side. So there are opportunities to validate services and products if you're a private company working in space through a CRADA, whether it's with the Marines or the Navy or service.
If I could pile in on that with Ann here, the tech bridge here at NSWC Crane has been very successful in getting these CRADAs through, and it's been a great tool, as Zach said. So if you have some ideas on things you may want to exercise or work, we will work with you and the tech. Ann will work with Julie Schaff and the tech bridge team to get your idea proper forward and get it CRADA instantiated, off and running.
Speaking of teams, I totally forgot to mention the team, join this whole team, which includes Ingersoll, who is known for making large subtractive machining tools. Meld, who obviously integrated their additive technology into the machines. Siemens, we're using their controls with Cinemeric 1, and then our execution team includes Lift and Astro America. So make sure I mention that. Thanks.
Sir.
Just was going to make a comment. I was at the Association of U.S. Army last several months ago with the Royal Australian Army, and the subject came up. We have a severe supply chain issue with the Navy as well as expeditionary forces, and we have for major overhaul, Japan and San Diego is our only main large overhaul bases, United States Navy in Indo-Pacific AOR. And the politics that was done on the bilateral between the Australians and the Secretary of Defense and the commands is we want to forward deploy as much of maintenance, repair, overhaul in the Indo-Pacific region to have and ensure capability that parts, components, supply, and equipment does not get returned to the United States for heavy depot, but is done as close to the line as possible. And a lot of that was in the discussion with the release of the latest unclassified National Defense Review. China is enemy number one. Russia, North Korea, Iran are the regionals, etc. But the takeaway from AUSA and the multilateral, bilaterals that you had with the various, let's say, allies within Indo-PACOM, the instructions were clear. Try to make sure you get your equipment, parts, and components built as close to the action as possible. So the way I look at it, as I explained earlier, you're not going to have a straight line across the Pacific connecting Japan and San Diego. You need to have Southwest Asia and Australia, New Zealand as one anchor. And I would assume that the next area would be the western flank of Southern Command as well, so that you have greater flexibility in that. So what you're doing on expeditionary is actually playing into the modernized think within the DoD in bringing the industrial complex or MRO equipment, products, supply chain modification closer to the warfighter to be ready to fight tonight.
Additional comment?
I mean, it's no accident. So the distributed force deployment or 2030 force deployment, it was first released, oh gosh, it's about 5 years ago now, for the Marine Corps, basically listed exactly that. It was the focus on the next fight. Be able to be prepared for peer level threat in the Pacific by 2030, and to focus on distributed, not just force, but also the supply, maintenance, and support for that force. And for the Marine Corps, what that means, being an expeditionary force, is being able to support essentially island hopping in the Pacific if need be, but broadly be able to work into the Navy's ecosystem, the Army, and the Air Force as well. And what we've seen since that initial force deployment in 2030 came out is now every single service has since then released their plans for by 2030, what will their services look like. And I should mention, every single force deployment calls out specifically 3D printing for supporting the supply chain and maintenance ecosystem of the future of 2030. So every service has some kind of plan in mind for 3D printing, and in most cases, at the expeditionary edge level.
Derek, do we have any questions from the folks online?
No questions.
If there's no further questions, I'd like to have the group give a round of applause for our panel. I thought they did a great job. And I would like to encourage, to socialize together. We've got food for lunch next door. You're welcome to join in, and our panel members will be accessible probably for the next, 20 or 30 minutes at least?
At least.
So feel free to get engaged in some of the networking. That's what we're here for. Thanks for coming. Please continue to look for these in the future types of events. We'd love to have you here. Thank you.